Unit 3D, Calculations with Uncertainty. Recall, absolute uncertainty is the range of values that the true value likely lies within. For example, saying 5.0 plus or minus 0.5 centimeters means that the true measurement of your object lies within the range of 4.5 to 5.5 centimeters with near 100% certainty. A good rule of thumb for determining absolute uncertainty is using 1/2 the smallest graduation of the measuring device. We've already seen that using a centimeter ruler, it is safe to use the uncertainty of plus or minus 1/2 centimeter, or plus or minus 0.5 centimeters, or plus or minus 5 millimeters. They're all equal. For a millimeter ruler, the uncertainty would be smaller due to the finer spacing of its graduation lines. When making a measurement with a millimeter ruler, we could say that the uncertainty is plus or minus 1/2 millimeter, or plus or minus 0.5 millimeters. The previous example shows us that a finer scale will give us more precise measurements and a smaller uncertainty. In some cases, such as triple beam balances, the uncertainty may be indicated directly on the machine on a sticker located usually on the back side. Remember, your confidence in using the device to accurately measure something may adjust the uncertainty up or down. Relative uncertainty indicates the confidence of a measurement or the quality of a measurement. It indicates how precise the measurement is. Generally, if the relative uncertainty is less than 5%, then you have a reliable measurement. You often hear this in political surveys where they are trying to predict the outcome of an election. They often hear the term 19 times out of 20, which calculates to 95% certainty. The formula for relative uncertainty is the absolute uncertainty divided by the measurement you made times 100%. Using our book cover, for example, from last lesson, we measured the book to be 5.25 centimeters plus or minus 0.05 centimeters, or 52.5 millimeters plus or minus 0.5 millimeters. The relative uncertainty would then be 0.5 millimeters divided by 52.5 millimeters times 100%, which gives us a relative uncertainty of 0.9524%, or roughly 1%, which is well within the 5% for a quality measurement. Another calculation for uncertainty is called the standard deviation, denoted with the symbol sigma. This measurement is used to determine the dispersion of multiple measurements. That is how spread out your data points are. If your measurements are spread out really wide across a range of numbers, then the measurement may be of poor quality. If the measurements are tighter together, then they may be better measurements. We call this a normal distribution of data points, and the shape is often referred to as a bell curve. This is a typical bell curve. The idea is that when you're collecting measurements, you will not repeatedly get the same value on each attempt, but rather due to variables, the measurements will have values that vary. Most of the values be very similar and very close to the mean average. And due to variables, you may have measurements that are not very close to the mean average, but those values that vary greatly should be seen less often as the difference in the values increase from the mean average. The thinking is that if your measurements are all good, they should be clumped together near the center, near the mean average, like the graph on your left. If your measurements are not as good, then the data points will be spread further away from the mean, as seen on the bell curve on the right. A small standard deviation value means the measurements are close to the mean average, which is represented by a tight bell curve. A larger standard deviation value means the measurements are far from the mean average, which results in a wider bell curve. One standard deviation is where 68% of the data points are found. Two standard deviations is where 95% are found. This is where we get the term 19 times out of 20, while 3 standard deviations represent 99% of the data points. Looking at an ideal bell curve, you'll notice that within one standard deviation, roughly 68% of the data points lie within that area. 2 standard deviations account for roughly 95%, while 3 standard deviations account for over 99% of the data points. An example of this is men's shoe size. The mean average for shoe size for men is a size 10. One standard deviation is 1.5 sizes. This means 68% of men have a foot size between 8.5 to 11.5. 2 standard deviations would be plus or minus 3. That translates to 95% of men having a shoe size between 7 to 13. 3 standard deviations equals plus or minus 4.5 sizes. 99% of men have a foot size within the range of 5.5 to 14.5. Anything below or above this would represent less than 1% population of men. Calculating standard deviation. Step 1. Take many measurements. 4 to 10 measurements are fine. Find the mean average, also known as the x-bar. This is where you take the sum total of measurements and divide it by the number of measurements. Note the symbol x-bar. Calculate the variance, denoted by the symbol sigma squared. To calculate the variance, find the difference between each measurement and the mean average. Square those values, then calculate the average of these squares. Take the square root of the variance. This value is your standard deviation.